Simple harmonic motion, SHM, differential equation derivation and solution ****. The above figure explains the complete derivation and solution of the differential equation governing simple harmonic motion, SHM. A particle performs SHM when it experiences a restoring force that is directly proportional to its displacement from the equilibrium position and always acts toward the equilibrium point. For a spring mass system, this restoring force is described by Hooke's law, which states that the force is proportional to the displacement and opposite in direction. By combining Hooke's law with Newton's second law of motion, the fundamental differential equation of SHM is obtained. This equation shows that the acceleration of the particle is proportional to the displacement but directed oppositely, which is the essential condition for oscillatory motion. To solve the differential equation, the angular frequency of oscillation is introduced, which depends on the spring constant and the mass of the particle. Using the standard method of solving linear differential equations, an auxiliary or characteristic equation is formed. The roots of this equation are imaginary, indicating that the motion is periodic and sinusoidal in nature. As a result, the displacement of the particle can be expressed as a combination of sine and cosine functions. This general solution contains two constants whose values depend on the initial conditions of the system. The initial displacement and initial velocity are then applied to determine the constants in the general solution. Substituting these values produces the particular solution, which describes the exact motion of the particle at any instant of time. From this displacement equation, the velocity and acceleration equations can be obtained through differentiation. The acceleration is found to be directly proportional to the displacement and opposite in direction, confirming the characteristics of SHM. The derivation ultimately demonstrates that the motion of a spring mass system is sinusoidal with a constant angular frequency. The time period and frequency of oscillation depend only on the mass of the object and the stiffness of the spring. Therefore, the mathematical analysis proves that a particle executing SHM oscillates repeatedly about its equilibrium position in a predictable and periodic manner, making SHM one of the most fundamental concepts in mechanics and vibration analysis.